Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, every week we profile some of the most amazing, jaw-dropping scientific developments which are revolutionizing our world and touching our lives. And in this week, once again, we're going to open the lines because this week is your week. It's open mic on Science Fantastic. Well, just last month I completed a whirlwind national tour going around the country to San Francisco, Los Angeles, to Chicago, to Boston, to Philadelphia, to Washington, D.C., and I collected a whole bunch of questions. So we'll answer a few of them, and after that we'll throw the lines open and you can get on Science Fantastic. Well, one question I got on several cities was, well, the universe, did it have a beginning or didn't it? Yes or no? Was there a genesis, an instant of time when someone or something said, let there be light? Or was it simply eternal, that the universe was always here and always will be? Well, it can't be both, right? One or the other. Did the universe have a beginning or not? Well, what does modern science say about this question? First of all, our universe had a beginning. We know this because we can actually detect the radiation from the Big Bang itself. This is amazing. When you turn on your radio and you're between radio stations, you pick up static. That static, a lot of it comes from Jupiter. Believe it or not, Jupiter creates much of the static we hear in the solar system, in our radios, when you go between stations. However, a certain fraction of that static also comes from the Big Bang itself. You are literally listening to the echoes from the creation of the universe. This is mind-boggling. Right there on your transistor radio, you could be listening in on the beginning of the universe. So our universe had a Big Bang. And our universe is apparently some kind of bubble. We don't know too much about this bubble, but we live on the skin of the bubble, and the bubble's expanding, and that's called the Big Bang Theory. Well, this is where it gets really freaky now. In quantum mechanics and also in string theory, we believe that there are other universes out there, other bubbles. And these bubbles are floating in a much larger arena. So even children ask the question, Mommy, Daddy, if there was a Big Bang and the universe is expanding, what is it expanding into? Well, if the universe is everything there is, then how can it expand into anything else? That's a contradiction in terms, right? But you see, if the universe is a bubble, it is floating in a much larger arena, an arena that gives you a timeless universe. And so we have many bubbles in a bubble bath of universes, and when these universes collide, bingo, we get the Big Bang. So the Big Bang is nothing but the change in the shape of these bubbles. Either the bubble bumps into another bubble, creates a bigger bubble, or the bubble fissions in half and creates a baby bubble. Now, this is very interesting because it coincides with, well, mythology. Every religion has some kind of theory about the origin of the universe. For example, the ancient Polynesians, or a myth of the ancient Polynesians had it that in the beginning was the great ocean, but in the ocean there was a coconut. And when the coconut sprang open, that gave birth to the universe. In the same way, the ancient Egyptians, in one mythology of the ancient Egyptians, in the beginning was the Nile River. And in the Nile River was an egg, and the egg hatched to create our universe. But then there are also some versions of Hinduism and Buddhism which says, no. The universe never had a beginning, it's timeless. There's only nirvana, timeless nirvana. And we are simply moving in this much larger arena, this arena called nirvana. Well, if this new picture from cosmology is correct, then we can meld together the two previous mythologies. You see, our universe had a beginning. Our universe, there was an egg, there was a coconut, and it hatched, and that's called the Big Bang Theory. But there's also a nirvana of hyperspace, and that is what the universe is expanding into. If the universe is three-dimensional, and it's expanding into something, it must be expanding into the fourth, fifth, sixth dimensions. And in string theory, which is what I do for a living, it expands into 11 dimensions. And so in other words, what is nirvana? Nirvana is 11-dimensional hyperspace. And we are just living on one bubble in an ocean of other bubbles. Now, you may say to yourself, this is all well and good, but what about proving it? What about experimental evidence? Well, there's several ways to approach this question. One is to build gravity wave detectors in outer space. Last year, the Nobel Prize was given to 3 physicists who pioneered gravity wave detectors, detecting the shock wave of the collision of 2 black holes in outer space. But when you put the detectors themselves in outer space, then you have an instrument big enough and sensitive enough to pick up echoes from the instant of creation itself. You see, when you turn on your transistor radio and you hear that static, a lot of that static comes from the Big Bang about 300,000 years after the instant of creation. That's when atoms began to form for the first time. Before that, it was too hot to create stable atoms. And so here's the name of the game. If we launch LISA, the Laser Interferometry Space Antenna, which NASA has on its books, it may be sensitive enough to pick up shock waves from the instant of creation, not 300,000 years after creation. No. At the instant of creation itself. We're going to get baby pictures of the infant universe as it emerges from the womb. And maybe, just maybe, we'll pick up evidence of an umbilical cord. An umbilical cord connecting our universe to another parent universe. And so this is the multiverse idea, that universes are constantly forming. Big bangs are happening all the time. The Big Bang is not just one event. It's happening all the time somewhere in this great multiverse of ours. There's a bubble bath of universes. And in this bubble bath, universes are being created. And so in other words, to answer the question, does the universe have a beginning or not? The answer is yes to both. Our universe had a beginning, but the multiverse is eternal. Okay, well, let's take a short commercial break, and after the break, we're going to go right to your listener phone calls. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open, so let's get right to it. Let's go to the first listener phone call.
Hi, this is Eric, calling from Fairbanks, Alaska, listening to you on 970 KFBX. And I'm curious, how come they can't calculate the trajectory of the Tiangong 1 space station and tell us where it's going to land? I mean, maybe it's a lot harder than I think it would be. But it also makes me wonder, it's like, how can they calculate the trajectory of, comets and asteroids and just, accurately and say that they're going to miss Earth? And how can we only hear about these near-Earth misses, after the fact they've happened? Or, we only hear about it maybe a day or a few days prior to the fact. So thank you. I really enjoy the show.
Okay, well, first of all, you're absolutely right that Newton's laws of motion and gravity are so precise, we can shoot a space probe right through the rings of Saturn. That's how precise our understanding of mechanics are. However, we are limited by the sensitivity of our instruments, and therefore tiny asteroids can sneak up on you, and you don't even know they're in your neighborhood till they're practically staring you in the face. And that's why often you hear in the news that, an asteroid just whizzed right by the planet Earth, between the orbit of the Earth and the Moon, and we were caught with our pants down. Well, it turns out that the bulk of research into cataloging these asteroids is done by amateurs. Let me repeat that. The bulk of sightings of these potentially killer asteroids are not done by professional scientists at all until fairly recently. Now, of course, we have some computerized telescopes scanning the heavens. But traditionally, it's been done by amateurs. Amateurs doing the thankless job of going out there in the freezing cold, photographing the night sky, photographing it a few hours later, and then comparing the two to see what moved. And that's why we're often caught off guard, because these objects are small, perhaps smaller than the size of a football field, very difficult to detect, and there's nobody out there every night watching the sky except for amateurs. And then, of course, we recently had the Chinese satellite, which plunged into the planet Earth. Fortunately, it broke up over the oceans, because most of the Earth's surface is covered with oceans. And the question is, why couldn't we predict exactly where that satellite is going to land? Well, several reasons. First, the satellite was tumbling, not in a simple orbit. Second of all, the outer atmosphere of the Earth is not perfectly spherical. It changes hour by hour. And so it's very hard to predict exactly when it's going to hit the air, because that entry point changes with time. And third, it's like a skipping stone. You know, if you get a stone and you throw it on the surface of a lake, it bounces. It bounces several times because of surface friction, a surface tension. But exactly where the rock falls into the lake is largely random. It depends on so many parameters, it's very difficult to predict where a skipping stone will finally land into the water. In the same way, these satellites are traveling at 18,000 miles per hour. When they hit the atmosphere, it's like a skipping stone. And again, you don't know precisely where it's going to land. Now, this is a practical problem as well, because we've had radioactive satellites come down with weapons-grade material. Cosmos 954, back in 1978, plunged back into the atmosphere of the Earth, carrying several hundred pounds of enriched uranium to energize a nuclear reactor in outer space. Fortunately, it broke up over northern Canada, and the CIA even sent a team of Huskies to try to retrieve parts of this top-secret Soviet satellite. And so, in other words, it's largely a crapshoot. We can't really predict where a satellite is going to land. Now, why should you care? Because the next big satellite to come down is the International Space Station. This gigantic object, the largest instrument of science ever built, costing over $100 billion in outer space, is going to come plunging down to Earth probably after 2028. That's when the great powers of the Earth are saying that there's no more money. Sorry about that. There's no more money to keep the space station up there. And it will break up. Now, the difference between the breakup of the International Space Station and the breakup of the Chinese space station is several-fold. First of all, the International Space Station is many times bigger. But second of all, we can aim it. You see, the Chinese satellite couldn't be aimed because it was tumbling and it was out of control, and the Chinese lost contact with it. However, we can actually aim the International Space Station to a degree, aim it slightly, so that we know more or less what continent it's going to land on, but we certainly can't tell if it's going to land on your backyard. It's going to be a gigantic, flaming meteor with all sorts of parts breaking off as it hits the atmosphere of the Earth. We suspect that about 30%, roughly 30% of the International Space Station will actually survive re-entry and plunge into the planet Earth, and hopefully will not wind up in somebody's backyard. Okay, let's move on to the next listener phone call.
John, KFQD, Anchorage, Alaska. If the universe is getting bigger, why are galaxies crashing into each other? And how come whenever I put a cup with a handle on it in the microwave, it always stops with the handle facing backwards? Thank you.
Well, let me answer the question about galaxies. Think of a balloon, and on the surface of the balloon, get a magic marker and draw a bunch of dots. Each dot represents a galaxy. So as the balloon inflates, the distance between galaxies expands because space itself is expanding. So how is it possible that we can have colliding galaxies? Well, it turns out that with your binoculars tonight, you can go outside with your binoculars, look in the direction of the constellation Andromeda, and bingo, you see a hazy patch of light with your binoculars. That is the galaxy Andromeda. Why is that important? That is the nearest giant galaxy to the planet Earth, and we are on a collision course with Andromeda. And it's not going to be pretty. Computer simulations show that it's going to be a titanic, catastrophic collision between two gigantic spiral galaxies. Now, first of all, why are they spiraling together at all? And that's because the expanding universe is an average effect. When you take two galaxies that are very close together, then the local gravitational pull is larger than the anti-gravitational dark energy that is pushing the galaxies apart. So we scientists, using the laws of Isaac Newton, can more or less predict how things are going to end. And for the Milky Way galaxy, it's not going to be pretty. We're going to see the collision of two gigantic spiral galaxies. And what's going to happen is the black holes at the center of the Milky Way and the center of Andromeda will merge to create a super black hole. In fact, if you look at Andromeda galaxy very carefully, you can actually see not one dot, but two dots. Two dots at the very center of the Andromeda galaxy, meaning that in the past, Andromeda probably already had lunch. We're probably already looking at a minor galaxy that was eaten up by the Andromeda galaxy. And that's why we see not one, but two blips at the very center of the Andromeda galaxy. Once our galaxy and Andromeda collide, and again, this is going to be about 10 billion years from now, so you don't have to worry about this. But when our galaxy and the Andromeda galaxy collide, maybe there'll be three black holes at the center. Okay, let's move right on to the next listener phone call.
Hi, Dr. Kaku. I'm Greg Conan from Newburgh, Oregon, and my question is, what do you think of the concept of moral bioenhancement, improving humans morally using biotechnology? Will it be implemented in the future? Should it? Thank you.
Well, the short answer to your question is yes. I do believe that at some point in the future, we should use our knowledge of DNA technology to enhance the human race. But, and this is a very big but, it of course is fraught with moral implications as well. We have the bad example of the Nazis. The Nazis tried to use the excuse of creating a master race and in the process conquering the world and cleansing the world of people that it considered undesirable, mainly Russians, communists, Jews, gypsies, people that were not, quote, Aryan, unquote. Now, of course, we're entering the age of DNA, where the mysticism and magic and folklore of the past is being replaced by hard evidence. Now, I think that in the short term, not much is going to happen, because at the present time, we cannot even clone a primate. That's how primitive we are at this point in terms of genetic engineering. We can basically engineer one or two genes at a time, and we can't even clone a simple monkey. However, with time and with a new technology called CRISPR, it's now possible to edit fairly accurately, almost like with a scissors and tape, to edit the DNA molecule. And this is opening up a whole new realm of medical possibilities as well as dangers. So one possibility is designer children. Designer children are going to be possible, not today, but in the coming decades, yes, it'll be possible for parents to begin to tinker with the genome of the children. Now, that has all sorts of implications. Well, let's take a short commercial break, and after that, we're going to continue a discussion of designer children and DNA technology on Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question, a very important question about the direction of genetic engineering. You see, in the past, there have been so many horror stories culminating with the Nazis and World War II concerning trying to cleanse the human race of undesirable genes. Well, now in the age of genetic engineering and a technology called CRISPR, it is possible with almost mathematical precision to cut and paste the DNA molecule. And some people fear that sometime in the future, let's say, for example, you're the parent of a high school kid, and you find out that your next-door neighbor's kid is genetically enhanced to have better memory and better study habits. Then it puts enormous pressure on you to genetically modify your child to be competitive with that other kid. And what's to prevent some back alley shop in Hong Kong from offering these services even if they are banned legally? I mean, we have a hard time banning illegal drugs. Think of the problems of banning illegal genes. I personally think there could be an illegal gene market, just like there is an international illegal drug market today, because of supply and demand. Unfortunately, there is a demand for drugs, and unfortunately, there will be a demand for shady operators who offer genes to make your kids more enhanced. Now take a look at the far future. In the far future, we are going to go to the stars. Exactly when, we can debate. But if we do go to the stars, we may have to genetically modify ourselves for survival's sake. For example, the gravity on Mars is about 1/3 the gravity on the planet Earth. And if we have a colony on Mars that is self-sustaining and permanent, we may have to have people who are genetically modified to survive in the lower gravitational field. Let's say we go to planets that have a different oxygen content. Planets where the radiation field is larger or smaller than it is here on the Earth. You can imagine all sorts of scenarios where we might have to modify the human race to adapt to these other conditions. Well, this is called transhumanism, and again, it's something that we cannot have today. I mean, we can barely manipulate one gene at a time, let alone a whole complex of genes to create new forms of animals. I mean, some people, for example, ask me, what about a pig with wings? Is it possible that we can genetically modify a pig so that it has wings? Well, in principle, yeah. But in practice, it would take hundreds, thousands of genes to be manipulated precisely in order to add wings to an animal. And that's simply not going to happen with today's technology. So let's not get carried away. Now, one technology, however, that is around the corner is trying to bring back prehistoric animals. I've interviewed scientists who've already brought back endangered animals, animals that are endangered that people thought were about to go extinct. Yes, we brought back some of them. But what about bringing back the dinosaurs? Well, it turns out that's probably not possible. We're not sure. But DNA from over 65 million years ago is extremely hard to find. But the mammoth, that's been talked about, to bring back the woolly mammoth. In fact, at Harvard, there was even a discussion of bringing back the Neanderthal. At that point, you have another set of ethical questions, because the Neanderthal is, well, in some sense, a human. They can feel. They can feel pain. They can feel anguish. They can feel the same kinds of feelings that we probably could. And therefore, how far do you go to create a new form of humans? Since this report was done at Harvard, some people have asked the question, if you were to create a Neanderthal boy or a girl, where do you put it? In a zoo or at Harvard? That's a question that we're going to be asking a lot in the coming decades. Okay, let's move right along to the next listener phone call.
My name is Boots Miller. I'm calling from Vallejo, California, and I'm actually not listening to a station. Wish I was. But, Doctor, here's my question for you. If you could in the spirit of Doctor Who and his ability to travel back and forth throughout time, at what point would you like to be able to travel in the TARDIS? To what point in time in the creation of the universe, either our past or our future, what do you think is the moment that you would love to go travel to, see, and witness? Thanks so much for the opportunity to ask a question, and I look forward to hearing what your answer is. Have a great day.
Well, you ask a very interesting question. Doctor Who, of course, gets into a telephone booth and is capable of rocketing back and forth through the annals of time, meeting all sorts of strange creatures and encountering many strange adventures. Well, that's probably not possible with today's technology, but you ask a question, where would I go if I had the chance to spin the dial and go anywhere in space and time? One place I would love to visit is the beginning of the universe itself. Now, of course, the universe was quite hot. The explosion was quite volatile. But let's say that we could be there a few seconds after the instant of creation, and we're protected by all sorts of shielding so we don't get fried by the intense radiation. That would be a magnificent event to be able to witness the creation of the universe itself. Another point in time might be to witness the creation of life on the planet Earth. We think that sometime around 3.5 billion years ago, the conditions were just right in the oceans, perhaps near a volcano vent. You see, volcano vents on the bottom of the ocean are quite hot, and microorganisms can feed off that heat because photosynthesis does not exist way down there at the bottom of the oceans. And so we think, and this is just a theory, that life on Earth first got started near the bottom of the oceans in a volcano vent before sunlight can create organisms that can use photosynthesis. That would be a great time to visit the planet Earth. Another time to visit the planet Earth would be 65 million years ago, because that's when a gigantic meteor or comet hit the Yucatan of Mexico and basically wiped out the dinosaurs. That must have been a catastrophic event. In fact, it was the largest meteor impact in 2 billion years. And that happened just 65 million years ago. It would have been quite an event to witness right there. And then, if I had another choice, I'd like to go back 75,000 years into the past. You see, something back then killed off most of the human race. Not the dinosaurs this time. We're talking humans. You see, any two humans are practically twins of each other genetically. If I take two dogs, for example, and I analyze their DNA at random, they're quite separated. But if I take two humans, analyze their DNA, we're almost twins of each other, clones practically. Now, the only way to explain the fact that we humans are so closely related to each other is to calculate when we had a common ancestor. You do the computer program, and the computer program shows that about 75,000 years ago, some event happened to wipe out most of humanity. Only a few of us, perhaps a few hundred, maybe 1,000, survived that cataclysm to repopulate the entire planet Earth. An amazing event. A handful of Adams and a handful of Eves repopulated the entire Earth. Now, what could have caused such a catastrophic extinction cycle? We think it was the eruption of the volcano in Indonesia, the Toba volcano, an event so catastrophic that many life forms in Africa were wiped out. And we think, but we cannot prove, that that is the event that almost wiped out the human race. So in other words, many times in the history of the human race, we have been pushed near the brink of extinction. You see, 99.9% of all life forms on Earth eventually go extinct. In other words, we have extinction facing us at some point in the future. That's why I say the dinosaurs are not here because they didn't have a space program. That's right. They're not here because the dinosaurs had no rocket ships to take them into outer space. We do. As a consequence, we should seriously think about having an insurance policy to make sure that life on Earth is not wiped out. Okay, well, let's move right along now to the next listener phone call.
Hi, Dr. Kaku. It's Denny North, calling from San Jose. My question is, considering the DNA changes observed in astronaut Scott Kelly compared to his twin brother Mark, how would you predict that the human species will evolve in space? Thanks, and I'll listen for the answer.
Well, personally, I think the media exaggerated it too much, making it sound as if the two twins diverged dramatically, but they were only small modifications. So we're running out of time, but get a copy of my book, The Future of Humanity, where I have a whole discussion about the dangers of radiation in outer space. Welcome back to Science Fantastic with Professor Michio Kaku. Every week on Science Fantastic, we profile some of the most amazing developments in science and technology. Things that are revolutionizing the way we look at the world and revolutionizing our life. And once again, in this hour, it's open mic. That's right, here is your chance to get back at the radio. Okay, well, let's move right along now to the next listener phone call.
Hello, Dr. Michio Kaku. This is Alan Rivas from Dryden, Washington. And my question is, tardigrades are known as the toughest creatures on Earth. So has there been any current research done with tardigrades in trying to explain the theory of panspermia? Thank you very much.
Well, you asked two very important questions. One is about the origin of life on Earth. One theory is called panspermia, the idea that maybe DNA was seeded on the planet Earth from outer space. And the other possibility is that microorganisms can actually survive the rigors of being in outer space. Now, it was once thought that life could not exist on the outside of a space capsule in outer space. We've sent many space capsules into outer space, and we try to sterilize them. But what happens if you have a microorganism that survives on the surface? Well, it turns out that when we shot space probes to the moon, somebody sneezed. Somebody sneezed at the facility where the space probe was being assembled, and that microorganism survived. Imagine that, a cold germ surviving on the moon. Well, since then, we found not one but several microorganisms and animal-like creatures, tiny little creatures that actually can survive the rigors of outer space, which was once thought to be impossible, but now, hey, that's what we find. In fact, scientists have deliberately created cultures of these tiny organisms, put them on the outside of space probes, and yeah, they can survive out there. They can survive the fact that there's a vacuum in outer space, and also outer space is radioactive because of the fact there's no atmosphere to absorb the radiation from the sun and from black holes. Well, let's take a short commercial break, and after the break, we'll talk about panspermia. That is, where did life come from? Did it come from the Earth, or did it come from outer space? Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we talk about science science that impacts on your life and our conception of the universe. Well, before the break, we had a question about panspermia, the idea that perhaps, just perhaps, life started not on the Earth, but from outer space, and that we were seeded somehow by DNA from the rest of the universe. How does that stack up? Well, it turns out that it's a theory that cannot be ruled out. In fact, there's several avenues that scientists have explored concerning whether or not life came from outer space. First of all, if you take a look at Earth and Mars, you realize that Mars, once upon a time, had great oceans. An ocean as big as the United States of America. A huge ocean. It had riverbeds. It had things that resembled the Mississippi River Delta. And Mars cooled down before the Earth did. So the solar system was formed about 4.5 billion years ago. And the planets began to cool down. Mars being farther away, cooled down first. And so the conditions to get DNA off the ground might have originated on Mars first, when the Earth was still molten. So let's say hypothetically that DNA gets off the ground in the oceans of Mars, and then a meteor strikes the surface of Mars and blasts rock into outer space, carrying tiny little pockets of DNA. These meteors then float in outer space for millions of years until the gravitational pull of the Earth brings them in, and these meteors then begin to seed the planet Earth. Now, in other words, if you want to see a Martian tonight, look in a mirror. We are the Martians, according to this theory. Now, can this theory be ruled out? And the answer is no, because it turns out that meteors from Mars have hit the Earth any number of occasions. This is amazing. If you take a look at meteorites, slice them open under very careful conditions, analyze their mineral content and air content, bingo! You find that some of them are a perfect match for Martian rock. Now, it turns out that asteroids are quite different. If you take a look at the carbon content, the iron content, the stone content of meteors, it turns out that most of them are quite different from the Mars rocks that we see on the planet Earth. And that gives ample evidence that we really are, in fact, looking at Mars rocks. One rock in particular, seems to have some kind of structures inside that look like microscopic worms. You can Google it on the internet. Yeah, these things really do look like microscopic worms. Other scientists say, bah, humbug. Nothing but crystals, tiny little minerals, crystals that look like microorganisms. That debate is still going on even today. Even today, scientists are debating whether or not if you crack open a Mars rock, are you looking at evidence of cells of ancient organisms or just crystals, crystallized crystals forming inside these rocks? Now, that's one theory, panspermia from Mars. However, there's another theory that's perhaps even more plausible, and that takes a look at the timetable. For example, the solar system is 4.5 billion years old. However, for about 500 million years, the solar system was very dynamic, with meteorites hitting the Earth all the time. Life was impossible in the oceans. There were no oceans, and the Earth was hit by meteors constantly. But then life starts about 3.5 to 3.7 billion years ago. So in other words, there's a window, a small window of opportunity, because before that window, the Earth was too hot to create life in stable form. The oceans probably boiled off many times in the past. And second, outside that window, life already gets off the ground. And so there's a narrow window between about 3.7 and 3.9 billion years ago to get life off the ground. Now, some scientists have said, aha, that window is too small. That window is only a few 100 million years wide. And it's too small to get life off the ground. Life gets off the ground very quickly after the age of heavy bombardment ends, and the solar system cools down to the point where we can get stable oceans and stable DNA molecules forming without them being boiled off with the next asteroid hit. So Fred Hoyle, a great cosmologist, actually believed this. One of the great cosmologists of the past actually wrote about the fact that life probably did not start on the Earth at all. It started in outer space. Now, to be fair, most scientists believe in the opposite point of view. If you were to take a poll, I would say that most astronomers believe that life started on the Earth, in the oceans, probably in a volcano vent, where there's enough energy to create the first forms of life without photosynthesis. Deep in the oceans, where there's no light, volcano vents give you enough energy and chemical processes to get the first DNA off the ground. But, hey, no one was there to witness this event, and so we won't know for sure for many a decade. Sorry about that. Okay, let's move on to the next listener phone call.
Hi, my name is Felicia Gaddis. I'm calling from Los Angeles. I'm not currently listening to the radio, but I wanted to ask you something. I'm very interested in string theory, and I wanted to know if you believe that there's a possibility that prayer affects the string theory, that it resonates, that it sends out a vibration that can change things.
Well, let's try to break it down into its basic components. First of all, what is string theory, and is it possible to influence these strings? First of all, when you look at particles of nature, you have electrons and protons and quarks and things like that. You find not one, not two, but literally hundreds of them, especially when you smash the proton apart. We have the Large Hadron Collider outside Geneva, Switzerland. It smashes protons at 14 trillion electron volts, an energy scale not seen since the instant of creation itself. And when you smash protons into each other, what happens? You get fragments. Hundreds, thousands of fragments, all with different Greek-sounding names. And it's hard to believe that Mother Nature at a fundamental level could be so malicious as to force us to contemplate thousands of subatomic particles at the most fundamental level. We think that the deeper you go into reality, the simpler it should be, not the more complicated and ugly. Right now, there's something called the Standard Model. The Standard Model does seem to fit most of the particles seen by our atom smashers. It is only a partial theory. For example, it has no gravity, and so gravity is missing in the Standard Model. A huge defect. Not to mention the fact that we have all these subatomic particles, hundreds of them, and we have 36 quarks, 19 to 20 free parameters that you can twist in like a dial on a radio. And Mother Nature, why would it create something so ugly? Some people say that the Standard Model is a theory so ugly that only a mother could love it. Now, even the creators of the Standard Model say it's ugly. Even they say their own creation is supremely ugly. So there's got to be something simple, elegant, beautiful at that fundamental level. And the leading candidate is string theory, which says that an electron is not really a dot at all. An electron is a vibrating rubber band, vibrating at one frequency. When you change the frequency of the electron, it turns into another particle, a neutrino. If you change the frequency of the neutrino, it turns into another particle, a quark. So you twang it enough, it turns into all the particles you see at the Large Hadron Collider when we smash protons apart. So in other words, why do we have so many subatomic particles? Because they're like musical notes on a violin string. Why does a violin string have so many musical notes? Because they're nothing but different vibrations on a single string. So what's beautiful is the string. What's messy is to catalog all the ways in which strings can vibrate. That's quite messy, and my friends spend a whole lifetime cataloging many of the vibratory modes of the string. Well, we'll answer your question about whether or not you can influence these vibrations after the break. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question, a very simple one, and that is, if the universe is made out of tiny vibrating strings, then is it possible to somehow influence these vibrating strings, perhaps, let's say, mentally? Well, the short answer is no. However, there is one way in which you might be able to use the human mind to influence matter. You see, the human mind is based on electromagnetism. We are, in some sense, a brain with electric generators creating radio. And radio is part of a theory of everything. It is just nothing but one frequency. So light itself, the electromagnetic spectrum, is nothing but one type of vibrations of a vibrating string. And so the question was, can you influence the vibrations of these strings? Normally the answer is no. However, recently we've been able to probe the brain and realize that the brain does have radio emissions, and they can be channeled using digital technology, which is also a vibration of the string. So in other words, in the future, you'll be able to simply think, and control objects around you. Take a look at my book, The Future of the Mind. I talk about how studies show that it's possible if you put a chip on the brain to have the chip then control objects around you. You can control your wheelchair. You can surf the web. You can write emails. You can communicate with people even if you are paralyzed. This is amazing. The brain can be unleashed electromagnetically. We can now upload memories, simple memories, download simple memories in mice. Now we're doing it on primates, and next on Alzheimer's patients. And so they'll be able to remember who they are and where they live. And so we are now interfacing the brain via electromagnetism, and the point is that all of them are nothing but vibrations of a string. Electromagnetism is a vibration of the string, and we're using one set of vibrations, that is electromagnetism, to eventually influence a computer, which can then control our environment. One day, when you walk into a room, you will mentally turn on the lights, mentally turn on the internet, mentally surf the web, mentally move objects around via your mind, mentally draw pictures, create artworks with 3D printers. In fact, from the outside, you'll look like Harry Potter, waving his magic wand, moving objects, creating all sorts of wondrous things mentally. That is the future of the Internet. The Internet is going to be replaced by BrainNet. And for more, go to my book, The Future of the Mind, which goes into some detail about how BrainNet is going to look like. It is the successor to the Internet. Okay, let's move on now to the next listener phone call.
Hello, my name is Sean O. I live in Portland, Oregon. In Interstellar, they experienced time dilation when they went down to the planet. Now, how would that work with quantum communication, which I guess my understanding is zero latency communication, instant communication between two people if one is, if their time is moving quicker or slower. Anyway, thank you.
Well, you have two effects involved there. Well, let's try to break it down. First of all, Einstein says that if you go faster and faster in a rocket, time slows down in that rocket. This is not science fiction. We measure this. In fact, we put two clocks. One clock on an airplane. That clock is atomically correlated with a clock on the Earth. When the airplane takes off, bingo, the clock on the airplane beats slower than the clock on the planet Earth. So time is not absolute. 1 second on the Earth is not 1 second on an airplane. It is not 1 second in outer space. So every time you go in an airplane, believe it or not, you're experiencing time dilation. Now, the question that was asked, though, is even more sophisticated, and that is quantum communication. If you take two electrons and they vibrate together, so they're touching each other, and then you separate them, an umbilical cord emerges between them, and they have, in some sense, knowledge of each other's state. So if you were to analyze the first electron, and it is spinning up, then you know that on the other side of the universe, wherever that other electron is, it's spinning down. The two cancel out because originally you had no spin at all. Now, believe it or not, this effect travels instantly faster than the speed of light. Einstein hated this idea. In fact, Einstein conceived of the experiment precisely to show that quantum mechanics is crazy, that quantum mechanics allows you to go faster than the speed of light. Well, this experiment has been done. You get two electrons or two photons, get them to vibrate together, separate them, measure one, and then instantly, faster than the speed of light, you know the state of the other. Well, sorry about that, Albert. You were wrong. But you had the last laugh. It turns out this information is random, so it is useless. So even though you now have something that goes faster than the speed of light, it is useless because you cannot send useful information faster than the speed of light. Like Morse code. You cannot send Morse code this way. Now, believe it or not, this is not the only thing that goes faster than the speed of light, but is also useless. Take a flashlight and sweep it across the night sky. I used to do this when I was a kid. Sweep a flashlight across the night sky and realize that the impression of your flashlight as it hits the outer space or the atmosphere, that image goes faster than the speed of light as you wave the flashlight in the heavens. But you see, it's useless information. You cannot send useful information faster than the speed of light. Each photon, each particle of light in the flashlight travels at the speed of light, even though the image of the flashlight casted on the night sky travels faster than the speed of light. So, in other words, Einstein has the last laugh. Yes, there are things which can go faster than the speed of light. Einstein was wrong on that. But net information cannot go faster than the speed of light. Sorry about that. Okay, let's move on to the next listener phone call.
Yes, my name is David Hawkins, and I'm calling out of Long Beach. And my question is, why does the total amount of normal matter in the universe equal the total amount of dark matter squared times dark energy? And I'm following this on Twitter, so thank you.
Okay, well, let's try to break this down into its basic components. First of all, matter consists of atoms, hydrogen, helium, lithium, things like that. We used to think that the universe was made out of atoms, but now we know that's not true, that most of the universe is made out of dark matter, and dark matter is a mysterious substance that is invisible. That's why it took so long for us to be able to confirm its existence. And it's related by E equals mc squared, E being energy, m is being mass. Well, let's take a short commercial break, but after the break, we'll continue a discussion of dark matter and what the universe is really made of. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a call about dark matter, so let me try to break that down. Back in the 1990s, we seemed to have a very compelling picture of what the universe is made of. Back in the 1990s, we thought that, well, the universe is made out of atoms. Simple as that. Electrons going around a positive nucleus. And perhaps the atom can be shattered to create cosmic rays and black holes and things. But the universe is basically made out of atoms. And the universe was also expanding. And the expansion was probably slowing down. No big deal. And it was a very pleasant, very stable conception of the universe back in the 1990s. Boy, were we wrong. Totally wrong. Because in the last 10, 15 years, we've had to rewrite all the textbooks. First of all, we know that matter is not mainly made out of atoms. Atoms are made out of electrons and protons, but there's something else, dark matter. And dark matter is 10 times more plentiful than ordinary matter. And is invisible. Invisible meaning that our detectors cannot easily detect it by telescopes and by our instruments. And that's why it took so long for scientists and astronomers to agree on the existence of dark matter. Then we have dark energy, the energy of the vacuum, which is pushing the galaxies apart, giving us the Big Bang. And it is not slowing down, as most textbooks said. It's speeding up. The universe is speeding up in its acceleration, and one day, perhaps, the night sky will be totally black, because the stars are so far away, light cannot even reach us from the depths of outer space. So, this is a very different picture than the 1990s, which said that the universe is based out of atoms, and the universe is expanding but slowing down. Now we realize the universe is made out of something different, dark matter, and the universe is not slowing down, it's speeding up. It is careening out of control. So what do we do with this? Well, we don't know. First, we want to capture it in the laboratory. That's why we have detectors around the world looking for the collision of dark matter with a proton. The proton will be shattered, and we look for the flash of light created by the shattering of a proton. So far, we haven't seen any, but there's always the hope. Then we hope to create dark matter with the Large Hadron Collider. And that has not been successful either. So right now, we're in a very strange period of time where we suspect that our textbooks have to be redrawn, rewritten, but we don't know how. That's where we are today. And if you in the audience ever figure out what dark matter is and what dark energy is, you will get the Nobel Prize in Physics. So what are you going to do first? You're going to tell me first, and then we'll split the Nobel Prize together, you and me. Okay, let's move on now to the next listener phone call.
Hello, my name is Andrew Horvath. I am in Phoenix, Arizona. I'm actually a science teacher, and I'm asking a question about health and the future. The future has always been a very interesting topic to me. I've been very excited about it, technology and everything like that. And so my question is regarding the medical field. Recently, I've seen some wonderful research about vegetable-based diets and things like that to help people. So I'm wondering, in the future, what do you think is going to be the most valuable tool for preventing medicine? Do you think people will be changing their diets? Do you think, one time I heard about, they could potentially have toilets in the future where I go to the bathroom in the morning and it checks all of my levels and it'll warn me that maybe it has found cancer cells or something in my urine, something along those lines. So what kinds of things do you think in the future are going to be in place to help prevent illnesses as opposed to maybe medicine that we use once we are already sick? Thank you very much for hearing my question, and I look forward to listening to your radio show.
Wow. Medicine is going to explode, absolutely explode in the future. First of all, you mentioned the smart toilet, which is going to render the word tumor obsolete in the English language. By the time you have a tumor form, you have 10 billion cancer cells or so growing in your body. It's too late. Surgery is required immediately. In the future, your toilet will pick up cancer genes, cancer enzymes, and give you a liquid biopsy. Up to the minute, liquid biopsy. No delays and no getting an appointment with the doctor and getting cancellations of your appointment. No, you'll be able to diagnose yourself and detect cancer decades, perhaps a decade before a tumor forms. So the smart toilet is going to be a form of preventive medicine which will render the word tumor obsolete. And then we'll attack tumors directly with advanced nanotechnology. We're going to arm individual cancer cells so that they seek out ordinary cells, so they seek out cancer cells and destroy them. And then when your organs wear out, we'll grow new organs from your own cells. These are called bioreactors. I've had a chance to take a camera crew to Wake Forest University and see these at work. We're talking about creating new organs of the body as they wear out. We can already grow skin, bone, cartilage, noses, ears, windpipes, bladders. That's today. Tomorrow, perhaps we'll grow the whole organism up to the brain. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to take you on a fantastic journey. A journey through space and time. A journey into our bodies. A journey into the world of science, the cutting edge of science. And if you want to be part of this, then give us a call. And also, I just finished a national book tour. My book is called The Future of Humanity. And I've had a number of questions that were given to me, and I'll try to answer another one of these questions. The question that sometimes I get is, why didn't Stephen Hawking, the great physicist, ever win the Nobel Prize in Physics? Well, if you think about it, that is ironic, because many lesser-known physicists who have done less spectacular work, they've won the Nobel Prize. So how come the Nobel Prize eluded Stephen Hawking, a physicist so famous that he's going to be buried in the Westminster Abbey? The Westminster Abbey in London is the most sacred church in all of British Christendom. Isaac Newton is buried there, not to mention many kings and queens of England, and including Stephen Hawking. So the question is, why didn't he ever win the Nobel Prize? Well, the answer is quite simple. The Nobel Prize is given for things that have been tested in the laboratory. Well, Stephen Hawking's main contribution is untested, and that is Hawking radiation. You see, black holes are black because they absorb all light. Nothing can escape. They're like the ultimate Roche Motel. Everything checks in, nothing checks out. However, Hawking showed, and this is his great contribution, that when you add the quantum theory of atoms to black holes, you find that black holes are not really black at all. They're gray. They emit a very faint radiation called Hawking radiation. That's why he didn't win the Nobel Prize. This is a great discovery because it was the first major application of the quantum theory, that is, a theory of atoms, to the theory of Einstein, a theory of gravity. These two theories usually hate each other, but Stephen Hawking showed that these two theories create a new effect, Hawking radiation. But it's too faint. It's too faint to be observed in the laboratory. So, we physicists believe it exists. It's out there, Hawking radiation, but the proof eludes us, and that's why Stephen never won the Nobel Prize. Okay, well, let's move right along now to your listener phone calls.
Hi, I'm Danny. I'm calling from Florida. My question is about your book, the Terraforming Mars part. Now, the only two examples I know about it are the Superman movie, where like everybody was floating up and hitting the ground and everything, and I think there was another movie where the guy survives on Mars, which he like basically made like a small little greenhouse and grew vegetables and stuff. I know the Superman movie wouldn't be like that. So if we were to do like a little bubble greenhouse sort of deal, and let's say we wanted, the target would be half of Mars, not all of it, just half of Mars, in a realistic sense, how long would that take to happen?
Well, you ask a question that a lot of NASA engineers are asking themselves right now. And that is, well, if you saw the movie The Martian, starring Matt Damon, he was left stranded on Mars with no backup, no supplies, and he had to grow his own food and sustain himself on the red planet. So one of the first things he had to do was find a way to get oxygen through a chemical reaction. Once you got that, then of course you have to get fertilizer for food, and he used his own waste products, yuck, for fertilizer. And then he started to grow plants on Mars because you had the carbon dioxide atmosphere. It's cold, but you can heat up the temperature using solar panels and agriculture. He was then the first one to create agriculture on Mars. Now, in the future, we'll do it using genetically modified algae. The carbon dioxide atmosphere is ideal to grow organisms. Plant organisms love carbon dioxide. And so it may be possible in the future to create a self-sustaining aquafarm or a farm of genetically modified organisms on the surface of Mars. That's one industry that you definitely want to get off the ground. Another industry is mining, because frozen water can be unfrozen, and that creates drinking water once you purify it, and you can separate it out into hydrogen and oxygen. So these are two reasons why you can use A, hydrogen for rocket fuel, and B, oxygen for breathing. So water would be the first major substance to be mined on the surface of Mars. This is beginning the process of terraforming Mars. So it's going to be very difficult. No one's going to terraform Mars immediately. The first settlements will just tinker with the mechanics of terraforming Mars. But the actual terraforming of the planet itself will take much longer. Now, how do you jumpstart it? If you can raise the temperature of Mars by 6 degrees, you will have a runaway greenhouse effect. How do you do that? You inject methane gas into the atmosphere of Mars. The methane gas captures sunlight, creates a greenhouse effect, which captures more carbon dioxide, and so you have a runaway greenhouse effect. So that's one way to self-sustain and terraform Mars. But, of course, it's not going to happen anytime soon. It'll take years, decades. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we also had a call about terraforming Mars, and he also mentioned Superman. So let me give you a historical link between Mars and Superman. Near the turn of the century, Edgar Rice Burroughs wrote the Tarzan series, for which he was famous, but he also wrote the John Carter of Mars series as part of pulp fiction back in the 1920s. Back then, he realized that Mars had a lower gravitational field than the Earth. So he said that if an Earthling were to go to Mars somehow, he would become somebody with superhuman powers. He'd be able to leap tall buildings in a single bound. He'd be faster than a speeding bullet. So Edgar Rice Burroughs said that this man on Mars, John Carter, would have the power of a Superman. Well, what happened was nothing happened until World War II comes along and people want a hero. And that's the origin of Action Comics and Superman. And the very first issue of Superman, it says very plainly that anyone from another planet landing on the Earth would have superhuman powers because of the low gravity. Precisely echoing the words of Edgar Rice Burroughs, creator of Tarzan, and John Carter of Mars. So in other words, the link between Mars and Superman is that Superman is in some sense a son of John Carter, a creation of the man who created Tarzan. Okay, well, let's move right on to the next listener phone call.
I'd like to propose at least one question. If the background microwave radiation from the Big Bang heats up the relative vacuum of deep space by 2.74 degrees Kelvin, then how can people like Dr. Lee Howe at Harvard, who were trying to reach absolute zero, completely evacuate the BMR from an environment so that the thermometer doesn't reach just 2.74 degrees Kelvin, but actually goes down to absolute zero? I found your presentation delightful on the future of humanity.
Okay, well, first of all, let's break down your question. It turns out that in outer space, there is an echo of the Big Bang itself. Believe it or not, you can calculate that the Big Bang was very hot, but in 13.8 billion years, it cooled down. So the temperature of the background radiation left over, the aftermath of the Big Bang, has a temperature today of 2.7 degrees above absolute zero. So children sometimes ask the question, Mommy, Daddy, how cold is outer space? Well, we know the answer, 2.7 degrees. Why? That's the temperature of the Big Bang today. Anything that hot back then could not go to zero today. We see residual radiation from the Big Bang at 2.7 degrees above absolute zero. But on the Earth, you can create in the laboratory temperatures below 2.7 degrees centigrade. Now, remember, that's the temperature of outer space. But on the Earth, it's possible to take out energy from a container of energy and drop the temperature below 2.7 degrees centigrade. And that resolves the paradox. And that is, if the temperature of outer space is 2.7 degrees, how can on the Earth you can get a chamber, a small chamber where the temperature inside is below 2.7 degrees centigrade? There's no contradiction whatsoever. And by the way, you can pick up this radiation on your transistor radio. If you turn your frequency on a transistor radio randomly, you get static. Believe it or not, most of that static comes from Jupiter. Jupiter is quite noisy in the radio spectrum, quite radioactive, but you can also pick up the Big Bang itself. This is amazing, that even a simple transistor radio can pick up residual leftover radiation from the creation of the universe itself. Absolutely amazing. Okay, let's move on to the next listener phone call.
Hello, my name is Charles Davis. I'm not listening to a radio station. I actually got your information off the internet. But I have a question for you. Was there ever a reverse law to the theory of light written by anyone, including Einstein, never published? If so, what would the implications of that be? And would that actually be I guess you would say, a link to relativity and quantum theory possible? Thank you.
Well, I think what you're asking is there a reverse form of light? I think that's what you said. In other words, anti-light or dark light. That light from a flashlight emits radiation, but a dark flashlight would absorb radiation, and blackness would come out rather than light. Well, the short answer is no, but let me explain why. First of all, there is something called antimatter, the opposite of matter, which is different charge. So the electron has negative charge. We learned that in elementary school. But the anti-electron, the positron, has positive charge. So antimatter has the opposite charge of ordinary matter. Now, light, however, has no charge at all. It's chargeless. And anti-light is light. So that explains, first of all, the mystery of black light. There is no such thing, because light and anti-light are the same thing. You can also answer the question about anti-gravity. Anti-gravity is gravity. That is, the antiparticle of the graviton is a graviton. The antiparticle is the photon of light is the photon of light. And therefore, reverse light or black light is not possible. However, recently, physicists were quite amazed that the universe itself is accelerating due to dark energy. Now, this is repulsive. Dark energy repels galaxies, and so it is a form of anti-gravity, which is amazing. There is a form of anti-gravity. However, what's the catch? The catch is it's extremely small. So small, you cannot make hoverboards or anti-gravity rockets out of it. Sorry about that. It is extremely tiny, but we do think on a scale of galaxies now, it is literally pushing the galaxies apart, cooling it down, and one day we may hit absolute zero or near absolute zero as a consequence of dark energy. Okay, let's move on to the next listener phone call.
Hi, this is Sean Markley from Shorewood, Illinois. My question is, as we become a level 1 or level 2 society on the Kardashev scale, which scenario becomes more plausible? Number one, us wormholing to other planets in the Goldilocks zone and searching our own universe for the continuity of the species, or number two, us wormholing into the past in an alternate universe to transfer folks into the alternate universe, if you will, for the continuity of the species. Appreciate any help on the answer, and thanks, and have a great day.
Okay, well, you asked a question about the Kardashev scale, which I write about. Kardashev was a Russian astrophysicist who wanted to catalog intelligent civilizations in outer space. A Type 1 civilization consumes the energy of a planet, like Buck Rogers. They control the weather. They can control earthquakes and volcanoes. Anything planetary they can control. Type 2 is stellar. They control the stars. They control the energy output of the star and nearby planets, like the Federation of Planets. The Federation of Planets in Star Trek would be a Type 2 civilization. Type 3 is galactic. They control the power of a black hole. And after the break, we'll answer the question about what it means if you can create a wormhole if you're a Type 1, 2, or 3 civilization. Can you go to the past or maybe the future? Welcome back to Science Fantastic with Professor Michio Kaku. Here's your chance to get on national radio and ask that question that you've always been wanting to ask. Well, before the break, we had another question that came in about the Kardashev scale and where we might take a wormhole to. Well, the Kardashev scale talks about civilizations centuries, millennia more advanced than us. A Type 1 civilization can control planetary power. They control the weather. They can mine the oceans. Type 2 has stellar power. They control the power output of an entire star. They've colonized all the nearby planets. And Type 3 is galactic. They control the power of black holes, and they roam across the galactic space lanes. Now, believe it or not, we can actually calculate when we will attain these incredible abilities. First of all, we know the energy output of a Type 1 civilization, and so we are about 100 years or so away from becoming Type 1. In other words, by 2100, we will become planetary with the ability to, for example, control the weather. In a few thousand years, we'll be Type 2. The ability to control the power output of an entire star, like in Star Trek. Type 3 is galactic, the power to manipulate black holes to roam the galactic space lanes. And that depends on whether or not you can get hyperdrive. So that may be, who knows, maybe thousands to 100,000 years more advanced than us. Now, the question that came in is, when are we going to get wormholes? And where are we going to go, in space or time, with a wormhole? Wormholes are shortcuts. They are allowed by Einstein's theory. In fact, Einstein himself in 1935 was the first one to find a wormhole solution of his own equations. A wormhole is a shortcut, like the looking glass of Alice. A shortcut that allows you to go from one point of space or time and another point of space or time. Now, when can we have these, and on what scale are we talking about? Well, as you can see, a wormhole has the energy of a black hole. Therefore, almost by definition, we're talking about type 3. A type 3 civilization that can roam the galactic space lanes, has access to galactic energy, and has the power of a black hole. And that is the power to rip the fabric of space and time itself. Now, where are they going to go? Well, one point is to go to other galaxies and other star systems and other sectors of the galaxy itself. So, perhaps Star Wars takes place in such a time, thousands of years more advanced than us. But what about going backwards in time? Well, that gets a little bit more dicey. Stephen Hawking, for example, admitted that it may be possible to create a wormhole to go into the future or into another point in space. But to go backwards in time, he thought, may be bordering on impossible. Well, we'll say a few things about that after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a call about the Kardashev scale of advanced civilizations and when we're going to be able to create wormholes. Well, wormholes are gateways through space and time made possible through energy scales of a black hole, meaning that we're probably talking about type 3, a galactic civilization capable of harnessing the power of dying stars and black holes to drill a hole through space and time. These are called wormholes, first pioneered by Albert Einstein himself in 1935 in a famous paper that he wrote with one of his students, Nathan Rosen. And then the question is, can you go forwards in space, like in a spaceship, or backwards in time? Well, Stephen Hawking had a point of view on this. He thought that wormholes to another point in space may be possible. The problem is graviton radiation. Gravitons are particles of light, and if you have enough gravitons, they can become quite dangerous and quite radioactive, and you can blow up the machine. So a wormhole machine may, in some sense, become unstable. Well, Hawking thought that maybe, just maybe, a wormhole machine taking you to a distant point in the galaxy was possible, that it was possible to control the graviton radiation as you entered the wormhole machine. But, he thought, to go backwards into the past, if you do the calculation, it turns out the buildup of graviton radiation blows up, and so maybe the machine explodes as you try to go to the past. Well, I've looked at that calculation, and I'm not convinced. First of all, how do you get the fact that the machine blows up when you go into the past in a wormhole? Because a light beam that falls in the wormhole winds up in the past, and then naturally goes to the present and goes into the wormhole a second time, and a third time, and a fourth time. That's why it blows up, because it goes through the wormholes an infinite number of times. But you see, I don't believe in that. I think you can only go through the wormhole basically once, not an infinite number of times, and so there's no contradiction with graviton radiation. Graviton radiation could, in fact, be finite. Now, why do I believe that you can only go maybe once through the wormhole? Because it depends on how you view going backwards in time. I personally think that the universe splits in half. The timeline forks into two rivers. One river takes you through a normal sequence of time, and the other river splits off, forks in the river of time, and that simply creates a new branch of a timeline. So all the paradoxes of time travel are resolved, and there are no infinities, no explosions or blowing up of graviton radiation. And so, in other words, time travel just might be possible. I'm not saying it is, because of course the calculation requires going to a higher mathematics called string theory, which is so advanced that we cannot answer the question yet. But in string theory, it's a quantum theory, time splits. And if time splits and you go backwards in time, you do not change your own past, which would create a paradox. You change somebody else's past, who looks like you, has the same mannerisms, but is your carbon copy. And so you've basically changed the fate of a parallel universe, but not your own. Sorry about that. And that resolves all the paradoxes of time travel. With a new outlook, you can read any time travel novel and resolve every paradox if you would simply assume that the universe forks into two roads every time you go backwards in time. Okay, let's move right along to the next listener phone call.
Hi, my name is Maria Ahmed. I'm from Orlando, Florida. And my question for you was, as we know, 95.1% of the universe is dark matter and dark energy. The rest of the universe is stuff that we can detect, visible light, visible energy. My question was, is it possible that there's an entire universe that's undetected within that dark energy and dark matter? Is it possible? It would be awesome to know. Thanks so much.
Well, you ask a question that's at the cutting edge of what we know about the universe. So let's break it down a bit. As we've mentioned before on this radio show, we used to think that the universe is... Oh, I think we're running out of time in this segment. Well, let's take a short commercial break then, and after the break, we'll answer a question. Is it possible there could be a parallel universe out there hidden in dark energy and dark matter? Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question, and that is, the universe we now know is much stranger than we previously thought. It is basically made out of dark energy, which is blowing the universe apart, and dark matter, which holds the galaxy together. Both are invisible, and both have led to Nobel Prizes. So the question is, if dark matter is dark and can hide things, could it basically hide a parallel universe? Well, probably no. However, it does raise some very intriguing questions. First of all, how do we even know there's dark matter out there? By looking at Newton's law of gravity, we know that the galaxy spins, but it spins 10 times too fast. If you take a look at Newton's laws of spin and calculate the centrifugal force of a galaxy spinning very rapidly, you find that it should fly apart. Therefore, something is keeping the galaxies together, even if Newton says they are flying so fast they should fly apart. And that's dark matter. So we use gravity to indirectly prove the existence of dark matter. Now, then the caller asked another question. If dark matter is invisible, is it possible that it's concealing something, like maybe another parallel universe? And the answer to that is probably no, because a parallel universe would have a lot of gravity. And gravity is how we even prove the existence of dark matter to begin with, because dark matter is invisible. Therefore, we see no presence of a parallel universe hiding inside the dark matter. However, there have been some surprises just in the last few years. One surprise announced just a few weeks ago was the fact that we can now have galaxies that are totally made out of dark matter, or galaxies totally made out of ordinary matter without the other. We used to think that dark matter and ordinary matter had to come together. But now we find that you can have ordinary galaxies with ordinary matter without that much dark matter at all, and vice versa. And so we're now realizing that the universe is a lot more mysterious than we previously thought. I should mention, however, that the leading candidate for dark matter is that it's a higher vibration of the string. We are the lowest octave of the string, but there are higher vibrations. The photon has a higher vibration. Its partner is called the photino. or little photon for short. And we think that is the leading candidate for what dark matter is made of. However, the question is more sophisticated than you realize, because in inflation theory, which is also a version of the Big Bang theory, inflation happens all the time at different points in the universe. So in some principle, it's possible to have universes inside universes, universes budding off other universes like a soap bubble, budding off other soap bubbles. And so then it's not so surprising if you can get a universe hiding inside dark matter. Okay, well, let's move on to the next listener phone call.
Richard Kelleher, I'm from Phoenix, Arizona, and my question is, I just read that the longest recorded electrical pulses from a dead brain were 10 days. How long does a brain consciousness last after death?
Well, you ask a very important question, a question, of course, that is a subject of not just doctors, but also ethicists, because the question is, when the brain dies, but the body survives, are you really dead at all? Well, first of all, it's usually considered that in a period of 4 to 6 minutes, brain tissues start to die because of lack of oxygen. And by the time 8 minutes have gone by, you are most likely suffering from a version of brain death. That is, neurons start to die, and after that, you are probably clinically brain dead. In other words, the EEG, the electroencephalograph, picks up no evidence of electrical activity, even though the body may still be intact. And this, of course, raises many ethical questions. Sometimes people in a coma, like, for example, because of illness or a car accident, could be brain dead, but their body is still alive. And then the question is it possible, therefore, they could be revived after being brain dead? And you ask an even different question. What happens under certain rare circumstances, like, for example, when the body is cold? The body can survive much longer in a state of suspended animation. So let's try to break it down really quick. And that is, medical ethicists are still debating after the case of Ms. Shivo, who was brain dead, but the relatives clung to the possibility that she could be revived, even though most doctors believe that there was no chance of her coming back because there was simply too much damage to brain tissue. Now, it turns out that some people in comas do come out. However, they are not totally brain dead. If you are totally brain dead with no electrical activity, chances are you're not going to be able to be brought back. However, this is an area which is very fuzzy because, of course, it all depends on how you define brain dead. And if somebody, for example, falls in a lake, in a frozen lake, then it's possible the person could survive much longer because of the cold, which stops the degeneration of brain activity. Okay, well, unfortunately, we run out of time. Good day.